Welcome to 15-minute data notes. Today, I want to go through k-means clustering, an unsupervised learning technique. Clustering is a way or a means to classify a data point or a set of data points. Classification as such is something that we as human beings do very, very easily, and we do it all the time. Every object that we see gets classified into a certain category, a certain color, certain circumstance, certain environment. We do classify all the time. How do machines do this? Machines do this in a few ways. One of the ways is we have a data set which has an image of a bird, and we say this is a bird, and we have 200 images of birds, and we say this is a bird, and 300 images of cats, and this is a cat. So it's labeled data set. And we feed it into the training algorithm, and finally the algorithm would need to predict any image as either a bird or a cat or neither. That's the general way. When we say clustering is an unsupervised classification algorithm, we don't provide a labeled data set to this algorithm. So a clustering algorithm checks all the data points and will be able to group that data point, mostly based on the distance from each other. And this is often a Euclidean distance. Let's go into this a little bit deeper. Before that, I just want to quickly specify that there are various ways to do this clustering. The one that I just described based on a distance is usually called the partition-based clustering algorithms. We also do a hierarchical algorithm, again, a clustering algorithm, again, based on distance. There's also a density-based clustering algorithms, also graph-based clustering algorithms. But here we will go a little bit deeper into the k-means partitioning clustering algorithm. K-means is a very simple algorithm, and it is a very intuitive algorithm. It is very easy to understand. And it is quite powerful in many, many applications. It has a varied number of applications. The infographic here that I have picked up from Wikipedia shows in a very nice way how it partitions the data continuously to arrive finally at the most optimal way of partitioning the data. How it does this is by minimizing the within cluster sum of squares, the Euclidean distance. So it minimizes that and then identifies the number of clusters. It's very critical that this number of cluster is always dependent on K. It is dependent on K, which is our number of groups that we need to specify. In this instance, it is it could be anything. I want the algorithm to specify my data or to classify my data into 2 groups or 3 or 4 or 5. There is no right value of K. This is one of the challenges of k-means as well. Let's now see how the k-means algorithm does this. Say, for example, these are our data points. They are all grouped into one group currently. Now, the k-means algorithm starts by initializing or randomly choosing data points from the data. It can be anything. there are various ways that k-means can, it does have the ability, especially in scikit-learn, we can specify certain initialization techniques for the k-means algorithm. And but currently, let's go via the just a simple k-means algorithm without such initializing techniques. So we randomly choose 3 points, and this could be anywhere, right? It could be anywhere. We choose so our k is a 3. We choose 3 points. They don't have to be equidistant, as in this case. They don't have to be in a particular part of the data. It is a random selection. So then what we do is for each of these data points, for each of them, we see which group or which centroid it is closest to, and then we assign it that particular centroid. So for this one, for example, is it closer to this or this? So we assign it in a similar fashion. So after assignment, say that we have most of, for example, these data points belonging to this group, and these ones as well, they belong to this. Then we have certain data points belonging to this, and then this. So our next step is then we calculate the new centroids. And how do we do this? We do this by calculating the mean. So the mean of all this group would probably come somewhere here. So we get our new centroid somewhere here and somewhere here. So we get our new centroids. Then we again pre-calculate the distances from all points, and we reclassify the data into these groups. So we have so the centroid has moved. Our centroid has moved. So we continue to do this process until there is no movement of the centroid, where we say we have reached at the optimal level of difference between all the different groups, and there is no movement of centroid. There is no better placement of centroid for this. And we then finalize that as our final grouping of data. So all these points get classified into these groups. So this is how we will arrive at k is equal to 3. Remember, k is equal to 3 groups. This algorithm will also give a result for k is equal to 2, k is equal to 4, no problem. So one of the challenges of this algorithm is that how to identify a good k for our data. So that is what we talked about, the initial centroid placement. We are not sure how to do that. There are, of course, there's a lot of theory on how to do this, how best to do this. And we usually use a k-means plus plus initialization in scikit-learn. There are also certain assumptions for this algorithm. For example, the k-means assumes that the clusters that are spherical, it also by default creates spherical clusters, because remember we are minimizing this sum of squares. So it's based on Euclidean distance, or even any other measure of distance is based on distance. So we get a nice spherical structure of cluster which is equidistant from our centroid. So the groups are always circular. By that, I mean, if you see this kind of grouping, this is the one of the, you can see how this can be a drawback. For example, this will be clustered as this and this, which is clearly not what we want. So it works well on spherically placed data. It struggles with similar density-wise data, and that's why there are other algorithms like dbScan, which can be used for this kind of data. Another problem with k-means is the outliers. And the reason is, for example, if there are points here very far away from the cluster, remember that we are again working with sum of squares, the Euclidean distance, the sum of squares. So then large outliers then add to the, and they can distort the centroid placement. And if there are a large number of them, they can really change the groupings, underlying groupings in the data, leading to misclassifications. We already spoke about specifying K, we don't know. There are certain methods like the elbow method, the silhouette method, to identify or get the CH method, the CH index. So there are certain statistical ways that we can estimate a good K and see what kind of structure is underlying in the data. So what all those methods do is for every value of K is equal to 2, 3, 4, 5, 6, however many you want. We calculate a certain score, a silhouette score, or a CH score, which are all plays on variability within and outside the clusters. And then each one gets a point, and then we see the final plotting of how it varies, and certain ways for us to identify the critical point and then say that this should be our K value. K-means is not so good with linear relationships, and because, like we discussed already, that it has to have Euclidean distance, it can't handle clusters that are separated by non-linear boundaries. For example, something that can go like this. It's difficult to find the good structure between that kind of data. Spiral data, we don't know something like this. It's hard to get the clusters. In spite of these limitations, though, k-means is one of the most, at least in all my data work, I have used it the most. It's one of the algorithms that I have worked on the most. For very quick tasks, there have been multiple tasks that I've used it for. One of the big tasks that we used it for was spatial data clustering. Like we plotted lat and long. And we have our data points, we quickly get our clusters, and we get the centroids. This is a very nice way to explore spatial data. However, it's important that when we are, planets as large spherical objects, so Earth's curvature becomes a thing. There is a way to use the Haversine distance, or for it, we can also use Manhattan. One of the variations of this algorithm, I used Google Map time from one location to another location as one of the criteria. In certain cases, the cluster centroids, right? The cluster centroids can give a better estimate for a particular problem, better than the mean. That can also happen. So I've done clustering and gotten the mean, better estimates for certain problems. Generally, for segmentation, I have used this. The customer data set, and we check the recency, how recently they ordered, the frequency, how many times they ordered, and what was their order value. And we give a rank based on all this, and we calculate one figure, and then we use these three and we feed it into our clustering algorithm to get our different levels of or different groups of customers, and for different marketing strategies. Another use that I've used it for is outlier detection. So if I just do a K is equal to 2 in a very noisy data set, and I explore what that K is equal to 0 and K is equal to 1, right? And so what is this group? This could be my noise. This could be my outliers. Also, we use it for data labeling and annotation, depending on whether depending on whether you want to feed this data finally into a supervised algorithm. So you have unsupervised data, you label, you annotate, and you label, and then you feed it into another pipeline as a supervised learning algorithm. So there are all these various uses that I have used it for. And it's a very useful tool to have in your data science toolkit. And I hope this has been useful. Thank you.